let's just do a recap of Green's theorem. So the setup of Green's theorem was where it says an R2 theorem. This kind of the context is R2, the xy plane, and there is a closed simple curve C through in a vector field. So we got the vector field is F P, and we know that, for a vector field, the x component of each vector is dependent on location, and the y component of each vector is dependent on location. So every location gets a vector associated with it, right? That's what the meaning of a vector field is. Every location xy has an associated vector. And then we've got a closed circulation loop through that in that vector field, and then and then the direction of the curve is such that if you walked on it, the interior would be to your left. So you're walking around, the interior is to your left, and that's essentially the same as counterclockwise. And then that closed loop creates a region. And we call it the interior, right? So this is the boundary, is C. C is the boundary. D is the interior. And C is a curve, and D is a region. Okay, and so then Green's theorem says this. It says that the circulation around the boundary is the same as the double integral over the region of this function, qx minus py. So we're going to hold off kind of defining or talking about the meaning of that function, but for now, just know that it's a rate of change. Say it's a rate of change of quantity called q. Okay, so it's a rate of change of quantity q, and it's kind of one of these multivariable rates, like we saw when we were doing double integrals to start with. It's a multivariable rate. So when you multiply that rate times dA, right? dA is like a little rectangle, dx dy. And when you multiply those two together, you get a little bit of quantity q. Or a little change in q. Right? Okay, so that's some sort of rate that we'll talk about next week. And then when you multiply that rate times the change in x and the change in y, or dA, you get a little bit of the quantity q, or dq. And then the double integral then accumulates all those little bits of the quantity across that region. And so that's the same as, that value is the same as the circulation line integral around the boundary. That's what this is. And so this is analogous to our fundamental theorem of calculus, the familiar basic one, but just like kind of stepped up in integral degree by 1. Okay? Hold on a second. Okay, sorry about that. All right. So how is it? So this side is like the integral from a to b, f x dx. It's like, so again, rate times little change in x gets a little change in a quantity, and you're gonna accumulate all those, sum up all the little bits of the quantity, and what do you get when you get that? You get the total net change. Both sides are net change of quantity. Oh, sorry. So let me instead talk about this as the rate of change, right? The rate of change of f. And then this would be lowercase f, sorry. All right, that's better. Right, so this is summing up like little changes in the quantity for f from A to B. This is final value of B, final value of the quantity minus the initial value of the quantity as a net change. So both give you net change. So notice this A and B, this is the idea of the boundary, right? Boundary. And so that's what we have here. That's analogous to the boundary around the region, right? The boundary is just looking at endpoints B and A. And then this integral from A to B is then considering all the x values in the interior. And that's what D is, the interior, right? So A to B, that's the interior. And that's analogous to D, everything on the interior, okay? So it's highly parallel, right? Just like stepped up 1 degree or one like kind of dimension of integral. Okay. All right. So, and we'll kind of hopefully it'll kind of tie in the loose end here when we talk about next week exactly what that rate of change is, and why does it make sense that you get the circulation around the boundary as equivalent to the net change of all these little bits of the quantity inside. Okay, so that depends on what this rate is. So that's kind of the mystery right now, is what is that rate of change. Okay, now another topic here to talk about is, so any questions on the kind of the overview of the Green's theorem there? All right, so what is this? So this rate function, this mystery rate function, right? So we don't need it yet, but there should be something familiar about this. Q, X, and P, Y, right? So our vector function is P and Q. And where have we seen this before? The idea of the Q function, the derivative with respect to X, and the P function, its derivative with respect to Y. That should kind of ring a bell, right? What bell does that ring?
Like it was on contour plots?
No.
Like when we were evaluating if things were conservative vector fields or not with Clairaut's theorem.
Right, checking to see if f was a conservative vector field. The way we could check it, we learned, was we could use Clairaut's theorem, right? Clairaut's theorem said fxy would equal fyx. And so what would that be? What is fxy? Well, here this would be like fx, so we would want py. And this is like fy, so we want qx. And so if that's true, if p, the derivative of p with respect to y and the derivative of q with respect to x are equal, that means we have some function f, some potential function, and we would say we have a conservative vector field. And that was one of all of our equivalencies and all the equivalent statements we talked about in a conservative vector field. This was one of them, right? The py equals qx. So if that's the case, if py does equal qx, what do you see here? What happens?
The integrand is 0.
Yeah, you get 0. Okay? And then likewise, if we have a conservative vector field, what is the circulation around a closed loop?
0.
Every circulation line integral in a conservative vector field is 0. That was another one of the equivalencies, right? One of the equivalencies of a gradient field was that qx equals py. Another one was every closed loop, every circulation integral has a value of 0. So it agrees, right? So if you have a 0 zero integrand, you're going to get 0, and that's agrees with the fact that our circulation would be 0 also in a conservative vector field. So with Green's theorem, if you have a conservative vector field, it works, it's true, but the thing just kind of falls apart, and it's just 0 equals 0, and there's really no interest to it. It's trivial, right? So Green's theorem then becomes interesting or kind of relevant, more relevant or worthwhile in a non-conservative vector field, right? When you actually have a value of your double integral and your circulation. Okay, so Green's theorem for conservative vector fields is really a trivial case. It's true. It satisfies Green's theorem just fine. Conservative vector field, 0 equals 0. Yes, okay. But there's nothing to it. There's nothing to do. There's nothing to talk about. Okay, so really the focus or the interest with Green's theorem is non-conservative fields, non-gradient fields. Okay, so let's do some examples. Okay, here's the first example. We want to verify Green's theorem. If if the vector field is y for x, and C is a triangle traversed from 0, 0 to 2, 0 to 2, 4 back to 0, 0. All right, so what does it mean to verify a theorem? So we know in Green's theorem that the circulation around C is equal to the double integral over d of q of x minus py. What does it mean to verify that? What would it mean?
If it's non-conservative.
Do both sides, both types of integrals, and see if they're the same.
Yeah, so to verify would mean we're going to calculate the line integral, and we're going to calculate the double integral, and we're going to check to make sure that they're the same for this particular scenario. That would be verifying the theorem. You got to do both. Verify means do both. So here we go. So we got a little work to do here. This is all good practice. Good practice over line integrals, double integrals. Lots involved here. So let's make the sketch. So starting at 0, 0 to 2, 0 to 2, 4, and then back to 0, 0. So what will the line integral consist of here? That loop? What will that look like, doing that loop?
C1, C2, C3.
Yeah, we're going to have to add 3. This is a piecewise continuous loop. It's totally distinct pieces that we have to do separately and add them together, right? So we'll do C1 plus C2 plus C3. Okay, so that means we need to parameterize the curve, right? Parameterizing the curve means writing a vector function that gives us every point on that curve. That's what vector functions are. Vector functions are curves, and so as such, they tell us every point on a curve, either in the plane or in space. So C1, let's do that over here. So C1, what will be our vector function for C1? So if it's every point on that curve, then what do we know about every point on that curve?
The x component would equal x, and the y component would be 0.
Yeah, so y would be 0. And then x is just going to vary from there to there, so we can just make that our parameter t. So x is going to vary. T, okay. C2.
0t.
So 0t.
2
2t.
t.
Yeah, so that's 2. Bar's in the way. All right, and so then this is the point 2,4. So now we know every point on that segment has an x value of 2. Y is varying, so we can say y equals t. And then for C3, this is a segment, right? It's not horizontal nor vertical. It's like a slanted segment. And so my recommendation for that was make your starting point, make your point the starting point. Like we're going to write the vector equation of a line. As the point on the line, use the starting point, and as the vector, use the vector that fills the whole segment, right? Starts at the starting point and ends at the ending point. So we're going to go 2, 4 plus. Oh, and I want to use let's use different symbols here. So instead of T for C2, let's use U. And and you could use T, it would probably be fine, but let's just use different symbols so we make them distinct. And then we'll use V. And so we're going to use the starting point plus our parameter times the vector that is for the whole segment. So what vector is that?
-2, -2.
2 and -4.
-2, -4, and that makes the vector function 2 minus 2v, 4 minus 4v. Okay, so I got my 3 vector functions, which define every point on my triangular loop, and I'm going to do these 3 integrals. So let's set up the first one. So what are the limits of integration for the first one? I'm going to go from what to what? So t goes from what to what on the first?
0 to 2.
Yeah, since t is the same as the x coordinate, it's just going to go from 0 to 2. And then we're going to rewrite f, y for x in terms of our, so I think y is 0, and 4x would be 4t. So that's our f, written in terms of our vector function. And then we need dr, which is, what, 1, 0. And that will be dt. Okay, and then plus. So let's do the C2. We're going to set up the C2. So C2, U goes from what to what in C2?
0 to 4.
This time 0 to 4. Yeah, U is the same as the y coordinate. It's going to be 0 to 4. And then we're going to have y comma 4x. So y is our U. 4x is 8. Dot. Dot du, which are dr, which will be
0, 1.
0, 1, and that will be du. And then finally, last one will be our C3 journey here. And so we've got we're going to write y is going to be 4 minus 4v. Again, rewriting f in terms of our vector function, and then 4x will be 4 times 2 minus 2v dot dr for this one, which will be -2, -4, and then dv. And what will v go from? From what to what?
0 to 1.
Yeah, so when you use this strategy for a segment, the strategy I tell you, where you use the starting point, and use the vector for the whole segment, then it will always be, your limits of integration will always be 0 to 1. That's a big advantage of doing that way. You never have to do any work to get those limits. Okay, so now we got the math to do, so let's look at this first one. 0, so we do the dot product. What's the dot product here?
0.
0. That's nice. And just a note here, paths on axes often are very advantageous because you'll have at least one 0, and zeros cancel things out. And in this case, everything fell out to 0. So if you had a choice of path, we do not have a choice of path here, but if you had a choice of path, choose axes whenever you can, because you have a 0. One of those coordinates will always be 0, and that makes for nice simplifications. Your second, if you have a choice in path, the second best choice is either a vertical or horizontal line or segment. All right, again, you get things are simple, right? So all the y coordinates, all the y coordinates are just u, and all the x coordinates are a constant. So that's the next best thing. If you have a choice of path, go for horizontal and vertical segments. So what's this dot product? Looks like 8.
8.
And it looks like that. So that's just going to be 0 to 4, 8 du. It looks like that's going to be 32. That's going to be 32. So this last one, so we're going to have equals 0 plus 32 plus this one. We have to write some stuff out here. Can't do this in our head. So it looks like negative 8 plus 8v minus 32 plus 32v. Please check my math. Speak up if I make a mistake. And this looks like negative 40 plus 40v which is negative 40v plus 20v squared from 0 to 1. Oops. So, okay, so we'll do this over here. So this is going to some side work on this third integral here. So this just the third integral equals negative 40v plus 20v squared. And I think that equals what? Negative 20? Make sure you plug 0 in. So you plug 1 in, you get negative 40 plus 20. Make sure you plug 0 in. That will not always give 0, right? There are plenty of functions that evaluated at 0 are not 0. So in this case, you do get 0, okay? So I think our total is what? So this whole thing is minus 20. So we get 12. That is the circulation. Okay, so 1/2 done. But actually more than a half, because we're going to find that this double integral is not as much work. It's a little bit of work, but not as much. Questions on computing the left side of Green's theorem here, which is, we've done this before.
C2 again?
What's that?
How do we find the C2 again?
This 2u?
Yes.
Well, it's this.
Oh, I see.
What happened? Am I still sharing my screen?
Yes.
What's this thing? Am I still sharing my screen? Okay.
Yes.
All right.
Yes.
You see it now?
Uh-huh.
Yeah, all the x coordinates are 2, and then y's just can vary up that vertical segment. All right. Any more questions about the triangle line integral? Okay, that's the left side. And remember, so verify, that's one thing that happened here. So the other part of verify is to do the other side and show that they're equal. So now we'll do that. Okay, so now I want to do the double integral over d of qx minus py dA. So let's do the qx minus py first. So here's our vector field. What is qx?
No 1.
Qx is 1. No, sorry. Qx is not 1. What is qx? This is this pq. So qx is 4. Py is 1. And so now we've got this region here. And we need to do the double integral over this region, and so we have choices, right? There's different ways we can do double integral. So what do we want to choose here? It's going to be the most efficient, straightforward way of computing the double, setting up this region for the double integral.
dx dy.
All right, dx dy. So like that's type 2, right? What about, so kind of our default is kind of type 1. Can we do type 1?
I'd rather do type 1.
Yeah, I think type 1 is a little more, it's kind of more default, familiar. So let's do that. Let's do type 1. So type 1 is dy dx. And so that's bottom to top, left to right. So we ask, is the bottom all one piece or is it split up?
All one piece.
All one piece. Is the top all one piece or split up?
One piece.
One piece.
Both one piece. Great. So bottom is y equals what? Y equals what is the bottom?
0.
0.
And the top is this function here. So it depends on your x value. What is the top? Y equals what?
2x equals y.
Yeah, so if you go from, it's the line from 0, 0 to 2, 4, that's clearly the line y equals 2x, right? So we're going to go from 0 to 2x here. And then those 0 to 2x's start where on the left?
0.
And end up where on the right?
2.
0 to 2. Double integrals, right? So double integrals, just like we did before, you got this triangular region. So that's all review. And so we're going to have 0 to 2. So this is 3. Integral of 3 dy is going to be 3y. And that from 0 to 2x dx. And so that's the integral from 0 to 2 of 6x. Again, make sure you plug 0 in. We do get 0 in. We do get 0 here. So just 6x dx. And that's equal to antiderivative 3x squared from 0 to 2 and just enough room equals 12. Got it. So the double integral of qx minus py over the region is equal to the triple or the single integral, the line integral around the loop. Questions on verifying the theorem? Okay, I want to point out one more thing here. So what do, just in the most general sense, this is a question from the past, what do double integrals calculate geometrically as
Net
in the most
volume.
general sense?
Net volume.
Someone saying net volume. Were you all thinking that?
Yep.
Yes, net volume. Remember, you have a surface, your multivariable function is a surface, that's f, over a region, r, and we're like accumulating the volumes of columns, right? Volumes of columns over r. And if f is ever below the xy plane, it carves out solids where your z values, the heights of those columns are negative. So those solids, the volumes of those solids get subtracted away. So net volume. And how is it that we could make that net volume be the same as the area of R?
Set the integral to 1.
The integrand, right? So if that function, that multivariable function, had a height of 1 everywhere, I cannot get away from this stuff. Okay, if the height of that function is 1 everywhere, f equals 1, then the volume that you get is for a solid with height 1 everywhere. And so the volume of that solid with height 1 is the same as what?
The area.
Area of the base, right? The area of the base, because the volume is the area of the base times the height. If the height is 1 everywhere, then the volume that you get for a surface of 1 is area of the base. So notice in this double integral, I'm gonna erase this part right here. I could have rewritten that as, since our integrand was 3, could have pulled that 3 out and written it as 3 times the integral over d of dy dx. And notice then what is my function now? My integrand function is now what? That's implied to be 1. So what is my double integral representing now?
Area.
Yeah, the area of D, right? The area of the region D. And so it's another way to calculate this. If you ever have a double integral of 1 and you can calculate the area geometrically, you don't have to do the integration, right? So this would be 3 times, what is D? D is a triangle. So you do 1/2 base. The base is 2. The height is 4. But then take 3 times that. 3 times the area of D. Lo and behold, the answer is
12.
12. Okay, so that was solving that double integral by noticing that we could apply this area idea, that if your function is 1, the net volume is the same as the area. But in a general sense, double integrals compute net volume, right? It's an R3 phenomenon. All the solids above the xy plane minus all the solid volume below the xy plane. Question. So 12 equals 12 equals 12. So 2 ways to do the double integral. You get 12. And then the piecewise circulation line integral is 12. Questions on this example? So this is verifying. Verifying means you got to do everything. You got to do both sides and show that they're equal. All right, can I clear this? Any questions? All right, next example. Next example is to find the circulation if C is this simple closed loop shown, right? On this parabola to 1, 1, across horizontally to negative 1, 1, and back down to the origin. So doing that circulation integral would consist of what?
Three integrals.
Again, we got to sum up. We got 3 pieces, right? Got a parabolic path, a horizontal path, a diagonal path. Okay, and so I just did one of these. I just spent 15 minutes doing one of these. I don't want to do another one of these. So do I have options? Is there a more creative way to get the value of this line integral, this circulation? Okay. Does this equal the double integral over d of qx minus py dA?
Yes.
Yeah, all the conditions for Green's theorem are met. We've got a simple closed loop in a vector field, and we're asked to find the circulation, so we can find the double integral over the interior region instead. And so which do you want to do?
Double integral.
Yeah, let's do the double integral. So let's do the double integral because that proved to be a lot easier last time, and I definitely think this one is going to be even longer for these pieces because last time we had one that was on the axis and one that was vertical, and that helped a lot. It still was work though, but this one has the parabolic path and a diagonal path and nothing on the axes, so this is going to prove to be at least as much work. So let's go with the double integral. So first we're going to do, let's find qx. Qx is what?
1.
1. Py is
0.
0. And now we have a choice, right? We have a double integral dA over the region D, so we have all our techniques. What are all our techniques for evaluating the double integral? We want to choose the most efficient or the best choice for efficiency here. So what about type 1? Type 1 goes from bottom to top first. is my bottom all one piece or is it split up?
Split up.
The bottom is split up. So if we do bottom to top, or a type 1 double integral first, or type 1 double integral, that's going to require a sum of two double integrals because the bottom is split into two pieces. All right, what about left to right first? Is the left side all one boundary, or is it split up?
Boundary.
All one straight line. What about the right side coming out here? All one boundary or split up? All one. So it looks like type 2 is going to save us and allow us to only do one double integral instead of two. So let's do type 2, which is what? dx first, left to right, then bottom to top. So left to right. So we need to write the equation for this line here, this segment. It goes from 0, 0 to negative 1, 1. What line is that?
X equals to negative y.
Yeah, y equals negative x.
Oh, sorry.
Oh no, you're absolutely right. X equals negative y. So that's perfect. So and that's actually what we need. What x equals what?
Negative y.
Negative y. And then the right boundary is our y equals x squared. So that means x equals what?
Square root of y.
Square root of y. And so those left to rights, they start at the bottom at what?
0.
0 and go up to
1.
1.
Wait, Professor, wouldn't that be from left to right, bottom to top, right? So it would be from 0 to 1 because it starts at the origin and then goes up to 1 instead of from left to right. It's not left to right, it's bottom to top.
I thought I said bottom to top. That's what I was thinking anyway. But what I said, okay, so what I said was the left to rights that we just found, the bottommost left to right is at 0, and then the topmost left to right is at 1. So that's what I tried to say.
Okay.
So we're accumulating the left to rights. We're accumulating these horizontal sticks, and the first one is at 0, and the last one is up at 1.
Got it.
So we were both right. Okay, so now certainly we found an easier path than the three separate single integrals, line integrals. And so we get x from negative y to square root of y. And then we get what? 2/3 x to the 3/2, or y to the 3/2, plus 1/2 y squared. And that from 0 to 1. Check my math, make sure I'm doing everything right. And so we get 2/3 plus 1/2 minus 0 minus 0. Always plug 0 in. If it's one of your limits, always plug it in and check. And that is 7/6. So what is 7/6 equal according to this problem? 7/6 equals what?
The area of the region.
Okay, that's true, but we're going to talk about that in a second. But what, in terms of this problem, what we were asked to find, what is 7/6?
The circulation line integral.
Yeah, it's the circulation, right? But we didn't calculate the circulation. We didn't do the circulation. We did a double integral. So how does it equal the circulation?
Because of Green's theorem.
Green's theorem, right? This is the whole point. Here in this problem, we used Green's theorem. We didn't verify it, but we used it. Okay? It's not offended. Its feelings are not hurt. Okay? It's quite happy that we paid attention to it. Okay? So we used Green's theorem, which means it asked us to find one expression. Green's theorem told us that was equal to something else, so we calculated the other thing instead. And then when we got the value, we say that value equals the expression or the line integral we were asked to find, and then we say by Green's theorem. 7/6 equals the line integral we were asked to find by Green's theorem. And we say that because we didn't actually calculate that line integral. We calculated the other expression, the double integral, that Green's theorem says is equal to the line integral. So if we had come along here and done this, we would have gotten 7/6, but that would have nothing to do with Green's theorem. That's just directly computing the line integral. Okay? So, but what do? We found the line, we found it an indirect way, right? Using Green's theorem means calculate the other thing. Calculate the double integral, which we know by Green's theorem is equal to the circulation line integral around C. So there's verify a theorem versus use a theorem versus direct computation, which has nothing to do with a theorem at all. Verify means what? Do both sides. Show that both sides are equal. Use means you're asked to do one thing, use a theorem, and you calculate something else. And then the theorem then guarantees that it's equal to the requested quantity. Direct computation, if you just follow the instructions in this problem, you don't use Green's theorem at all, and you're just directly computing the line integral, and Green's theorem isn't involved. Does that make sense? Difference between verify a theorem, use a theorem, and not using a theorem at all, which is direct computation. No theorem. Okay, and then someone said that 7/6 is something else. If you noticed, when we started doing this double integral, you might have noticed something special. What do you notice?
1.
The integrand is 1.
Yeah, the integrand is 1. So that double integral, not only is it calculating the double integral over the region D, and not only is it going to give us the circulation around the boundary by Green's theorem, but it's also going to give us what? Area, right? So because the integrand turned out to be 1, 7/6 is also, it's like a bonus, right? It's had nothing to do with what we were asked, but it's going to be the area of D. Now, so don't feel bad that we should have just found the area instead of doing the double integral. No, we can't just find the area because it's got this parabolic side to it. So there's no formula that we could have plugged into to get like this wedge with a parabolic side. So we had to go ahead and compute the double integral to get that area. All right, questions on this example? Okay, so one more. All right, now I want to find the circulation.
Ashbrook,
Yeah.
I just wanted to ask if Green theorem also works with another if we wanted a third variable involved with Green's theorem, like Z, would it still work?
It's not. Yes, there's a version of that called Stokes' theorem, but it's not Green's theorem. So Stokes' theorem is the three-dimensional version of Green's theorem.
Okay, thank you.
And we don't have enough in 267 doesn't get to Stokes' theorem. In 272 we get to Stokes' theorem. It's pretty much the last thing we do. But 267 does not get to Stokes' theorem. So, but yes, good question. All right, so now I want to do the line integral around this loop, which is the slanted ellipse. Slanted ellipse, according to this equation right here. And so it says evaluate the line integral. So what about doing that directly? What would that consist of? What would we have to do this directly?
Parameterize the curve.
Parameterize the curve. Write a vector function. How about that? Slanted ellipse, according to this equation. X squared plus 3xy plus 4y squared. No, I don't want to. I don't want to. Yes, me too. I don't want to. Bad. This is might take some computer system, or this might be like a group project, or something like that. All right. So, we have another choice, maybe. Okay. Any questions?
Double integral over the area.
Double integral over that made sense. I hope you liked it. I think this subject's really cool. All right, and to do that, oops,
I just had a quick.
QX
Sure.
minus PY.
It's kind of just like real world application.
DA.
It's like
To do that, I need to find limits of integration for this region D. How about that? Limits of integration. You want to use type 1,
can't
type
think of
2, or
something,
polar?
but
not everything. There's lots of things in math that are just beautiful in and of themselves, and not everything has to have a real world application. But there may be. There may be something. Yeah, I should have said that. It should have said that.
Oh, okay.
Yeah.
It's just
It
Math
should be
has
it
beauty
needs to
in
be
and of
specified
itself,
but
and
yeah, you're right. And so we appreciate
is
that.
can you
And
just,
yes,
add
real
a
world
negative
applications
sign
are
if it's clockwise?
incredibly
That's right.
important. So
They're not
whatever,
everything.
whatever your positive orientation is,
They're
if
not
you
the
go
whole
the
lot.
other
They're
way,
not
you'll just
everything.
get the opposite.
Okay, cool.
That's
Thank
right.
you.
So what about writing limits of integration? So we need limits of integration for this region, which is a slanted ellipse. I don't want to do it. Terrible. Another group project, right? This is hard. Or can you use a computer? So this is going to be, polar is not going to be good because you need to find r as a function of theta. R changes as you go around. And certainly this is not going to be, writing y as a function of x or x as a function of y. Not simple. So we're kind of getting stuck here. Anybody notice anything? What is QX?
2y.
2y. Sorry. I got this backwards. This is py. I went py and qx. What is py?
Also 2y.
2y, qx, 2y. What happened? What's going on here?
It's a conservative field.
Conservative field. And we're doing a closed loop, a circulation in a conservative field.
So 0.
Yeah, right. So all circulation line integrals in a conservative field are 0. So we say, phew, right? We dodged a bullet there, right? Because doing this directly, trying to parameterize that curve or write limits of integration for that region, not friendly, not good. So because it's a conservative field, though, it doesn't matter how bad that loop is. Every closed loop is 0 in a conservative field. So with these Green's theorem problems, with these circulation integrals, moral of the story, always check to see if it's a conservative field first. Because if it's a conservative field, you're done. Your circulation is 0.